at Stanford University.
All right, the last time I started to set up a little bit of mathematics, some very elementary mathematics, but let me just review it, and then we'll use it. The purpose of using it today is going to be to get to the Boltzmann distribution. The Boltzmann distribution is the probability distribution that a system in thermal equilibrium with a heat bath, remember what thermal equilibrium means? It means that a small system is in contact with a large heat bath. When we focus on that small system, energy goes back and forth. There are fluctuations in the energy. Over time scales which are sufficiently long and not very long for most systems, the energy will have some average value in the subsystem, but it will also fluctuate some, and so there will be a probability distribution. That probability distribution is the special probability distribution associated with thermal equilibrium, and we want to try to find out something about it. In fact, it happens to have a rather universal form, which is called the Boltzmann distribution. Sometimes the Maxwell-Boltzmann distribution, but it was really Boltzmann who really got it right. So let's begin with the idea. Instead of a heat bath of arbitrary kind, it turns out to be simplest. This is a mathematical convenience. This is not a deep fundamental point. We could take the heat bath to be anything, but it turns out to be simplest if we're interested in a system that we will call A. The only thing about the system is we want it to have a lot of degrees of freedom. In terms of molecules, we want it to have a lot of them. That's the system. It has a collection a collection of states. Let's put an axis over here to represent the states of the system, and the little tick marks here could represent the energy levels, the possible energy levels. If the energy is continuous, if it's a continuous variable, as it really is in classical mechanics, we'll have to take that into account. But for the moment, let's just simplify things and say there's a discrete collection of states, which we label with an I. The lowest one is called the ground state, the state of lowest energy, and up we go. In most systems of interest, there's no ceiling to the energy levels. They go up and up and up. So there's an infinite number of energy levels. And in place of a heat bath, well, not in place of a heat bath, but as a special case of a heat bath, which is particularly easy to analyze, we just imagine a bunch of copies of the same system. Why make things more complicated than just repeating the same system over and over again? No particular reason, and as I said, that does make things easier. Now, in order that A comes to thermal equilibrium, of course, in the heat bath of all the other replicas or copies of A, it's necessary that heat can be exchanged, or that energy can be exchanged between them. And that, for example, could happen in a variety of ways. Possibly molecules go back and forth through a permeable partition. Other ways, radiation could go back and forth. Whatever the way that energy goes back and forth, let's just indicate it by drawing little pipes connecting all of the copies together, and we'll say that there are n copies. N is a very big number, and in the end, we'll really be interested in what happens when n goes to infinity. Now let's focus on a set of numbers, which we can call occupation numbers. Now, if you've heard of occupation numbers before, in particular in the context of quantum field theory, don't confuse it. This is a different concept. The question is, how many of these boxes occupy a particular energy level I? So to represent this, we could draw some lines The lines could indicate the first box here is in state 1, 2, 3, 4, 5. I equals 5. The second one, and of course this changes with time. They rearrange. But at a given instant, we could imagine drawing lines, and those lines would simply tell us this box is in this state, this box is in this state. Now, of course, you can have several boxes all in the same state. No reason why there can't be two boxes in the same state, or 3 or 4 or 5. And so we can define a collection of integers, the number of copies, let's call it a little n. Little n is the number of copies drawn from big N which occupy the state I. I'm not sure that the copies occupy the state or the state occupies the copy, but you know what I mean. So that's Ni, and of course, most of them are 0. Most of them are 0, the Ni's, because there's an infinite number of states, but only a finite number of boxes. And besides, I'm going to also assume that the total energy of the whole collection is fixed. Let's call it E total. And I might as well now not even define E total. There's an average energy that each box has. Since they're all identical to each other, when they come to thermal equilibrium, they will all have the same average energy, just by symmetry. So they'll all have the same average energy. And of course, the total energy, which is fixed, frozen, will simply be N times the average energy. Let's write it down. E total is, of course, N times the average energy in each box. I'm not going to always indicate that I mean averages. I've gotten tired of using this symbol like that. It takes too much space. I will sometimes use the overbar, and sometimes I'll just ignore it. Please ask me if you're confused about whether I'm talking about averages or not. But since the total energy is fixed, it must be N times the average energy in any given box. So this is one fact. What other facts do we have? Well, first of all, each energy level has a certain value. These N's are subject to two constraints, and really only two constraints. Things fluctuate, energy goes back and forth, things change with time, but certain things don't change. First of all, the number of boxes doesn't change, by assumption. That's our system, a fixed number of boxes. This is the number of boxes in the ith state, and so it must be the case that the sum over I of n sub I, that must equal the total number of boxes. The number of boxes in the first state plus the number of boxes in the second state, and so forth and so on, must altogether add up to n. And obviously, since n is bounded and can't get to, since n is bounded, none of these n sub i's can be bigger than n, and that means most of the states must be unoccupied. Most of the n's must be 0. Most of the little n's must be 0. But that's okay, nevertheless. First statement. Next statement. If we take the number of boxes in the state I times the energy of the ith state, that gives us the total energy. Sum over I, sum over... Let's be very clear now. This sum is not the sum over the boxes. It's the sum over the energy levels. The number of boxes in the state I. So I labels states, not boxes. So don't get confused by that. Second, the number of boxes with each energy level, when added up, has to add up to the total energy. So that must add up to either E total, depending on the way we want to write it, but we can also remember that that happens to be N times the average energy of any given box. The energy, total energy, and the total number of boxes are fixed and frozen and will never change in this discussion. And so these can be thought of as constraints. Whatever we do, we will not change these things. Now, the next question is, how many ways are there, given a set of occupation numbers, how many ways are there that those occupation numbers can be realized? Let me just give you a simple example. Supposing there are a bunch of states and only 2 boxes. And let me take the case N1, that's the ground state, is equal to 1, and N2 is equal to 1. How many ways are there that N1 can equal 1 and N2 equal 1? Just one way. Both boxes are in the first state. So we would represent that by drawing a line like that. 2 lines at this point. On the other hand, what's the, just to illustrate the concept, what's the number of ways that N1 can be 0? That's what I want.
Wasn't that N1 equals 2 and N2 equals 0?
Say it again.
N1 equals 2.
Yeah, N1 equals 2.
And N2 is 0.
And N2 is equal to 0. That's the number of ways. It's also 1, isn't it?
No.
No.
The first one was 2.
What?
This is correct. Correct.
This is correct for what you proved, yeah.
Sorry, I thought I right. For what I drew, N1 is 2 and N2 is 0. Good.
The other way.
Right here. Okay. How many ways are there of making N1 equal to 2? One way. Okay. In general, there may be many ways of doing it. Many ways of having a given set of occupation numbers. For example, we could have N1 equal 1. Let's see. And
Sum has to be 2.
sum has to add up to 2. And what's another possibility? Let's see.
Yeah, you can have them both. One go to 1, the other is.
Yeah, one go to 1, the other go to 2. Right. So N1 is 1, and N2 is 1.
Right, now you want one to go to.
Right, so now we have either this situation, or, what's the other situation? Let's draw gluing. Just the reverse. Not the reverse, the
Inverse.
converse, the obverse. Because the first box goes to the lowest energy level, and the second box goes to just cross them over. All right, so there are 2 ways to have N1 equal 1 and N2 equal 2. In general, there will be a multiplicity of ways of obtaining a given set of occupation numbers. What is that multiplicity? What is the multiplicity in general? I told you what the answer was last time. I assume you've all worked it out. It's not very hard. It's a simple combinatoric problem, standard combinatoric problem, and I'm not going to prove it here. We'll just write down the answer. Let's call that number, I just call it number. The number of ways that the energy can be partitioned up among the boxes such that we have a given set of n sub i's. And that is equal to n factorial divided by n1 factorial, n2 factorial, n3 factorial, dot, dot, dot. In other words, let's write it as n factorial over the product over I, the product over all the states of the occupation number n sub I factorial. That's the answer to that combinatoric problem. Now let me tell you first of all that in the practical applications these kind of things, think of them as functions of the n's. First of all the n's in the problem are going to be very large. Capital N is a huge, huge number of copies. So huge that the occupation numbers of every state will also be assumed to be large. Now, of course, that's a bit of a contradiction because we don't expect to have occupation numbers way, way, way up on the top. But those occupation numbers which are non-zero and non-negligible will typically be proportional to n itself. If you double the total number of particles, the total number of boxes, you will double the number of boxes in each one of these configurations. So by making capital N big, we also make the little n's big. One fact. Second, think of this object over here as a function of the little n's. It's a highly peaked function. We're not going to prove this, I'm just going to tell it to you. When the n's get very, very, very large, actually I will wind up doing a calculation for you which will show you this fact. But when the n's get very, very large, if you were to think of this quantity over here as a function of the n's. Now the horizontal axis stands for many horizontal axes, namely all the n's. Typically this number here is a very sharply peaked, I didn't draw it sharply enough. As the n's get large, it becomes a rather sharply peaked function so that it doesn't fluctuate very much. It doesn't fluctuate nearly as much as the size of n itself. That means when the number of boxes gets very, very big, you can be pretty sure, and as the number of boxes get bigger and bigger, you can get surer and surer of what these little n's are. Now, more specifically, that sounds a little ridiculous. Can I tell the difference between having a box N1 with 5,271 occupation number versus 5,272? No, of course not. What I mean by saying it's narrow is that it's narrow on the scale of capital N itself. In other words, that you can be pretty sure what the value of n sub I over n is. That the n's don't fluctuate very much. As numbers get bigger and bigger, they get tighter and tighter. That means that for very, very large systems, these n's get pretty definite, or at least the fractional n's become pretty definite. All right, that suggests that we give them a name, the fractional n's. Let's give the fractional n's a name. Let's call it P of I. Why P? Well, if you have a large number of identical replicas, subject to some fluctuation, but you know the ratio of the number of each type of box to the total number, it makes a lot of sense to think of that as the probability that any given box is in the state I. What is probability, after all? It's essentially the same thing as saying you have a large number of replicas of the same thing, and you take the ratio between each given outcome relative to the total number of copies that you have, and that's what's called probability, or at least that's one way of representing probability. So n sub I over n can be thought of, or at least n sub I over n at the maximum up here, the most likely value of these occupation numbers, they can be identified with the probability that any given box is in the state I. That's the basic tool. It's as simple as that, more or less obvious. So we'll define P sub I to be little n sub I over n, and now let's rewrite the two constraints that are up there. The two constraints that are up there are, first of all, the sum of n sub I equals n divided by capital N. And what does it become? It becomes the sum of n sub I over n is equal to 1, or simply the familiar statement that the sum of the probabilities adds up to 1. Just divide through by n, and that tells us the sums of the probabilities add up to 1. Not a big surprise. The other statement, let's write it down, summation over I of n sub I e sub I equals capital N times the average energy in each box. I'll continue to use the overbar notation for a little while until I get tired of it. Now divide this by capital N. This becomes n sub I over n, and that's p sub I. The average, in fact, this is a much more general formula than just for the average energy. In general, the average of a quantity is the weighted sum over the states of the system of the probability of the ith system times the value of that quantity in the ith state. In this particular case, it's the energy. So these two constraints, or those two constraints up there, become the very familiar...
Is that the total energy?
No. No. Okay, let's go back over it again. It's not the right-hand side, is not. We started with sum of I, n sub I, e sub I is equal to the total energy, but the total energy is n times the energy of any box.
Oh, energy, okay. Yes.
And then we divide it by capital N. Okay? So I have gotten rid, effectively, of the large number of boxes, but of course the large number of boxes is still a problem here because they're going to tell us it's the large number of boxes and how they equilibrate the energy between them that's going to tell us what the energy distribution is, what the p sub i's are. So far I haven't told you what the p sub i's are. Okay, so these are constraints. Now, what are the p sub i's? The p sub i's are simply the values of the n's, not the values of the n's, but the ratio, the fractional value of the n's, at the most likely value of the n's. In particular, if the system gets very, very big, it's extremely rare to find yourself away from the most likely set of occupation numbers. And as the system gets bigger and bigger, the ratio of these occupation numbers gets more and more tightly constrained to the value at the maximum of this function. So, we then have to find the maximum of pound here. I don't know when I started calling it pound, but a long time ago. The maximum of this thing as a function of the n's subject to these constraints can either be written this way or the way on top. This is the mathematical problem. And it sounds like a terrible mathematical problem, but fortunately it's extremely easy, surprisingly easy. I'd say it's a couple of lines. Now, the first thing to do, you don't have to do what I'm going to do. There's other ways to do it. I'm going to take you through the most efficient procedure, which I didn't invent. It was invented a long time ago. Probably people tried other procedures. But the most efficient procedure begins by saying, if you're maximizing pound, you can also substitute maximizing its logarithm. Why? If a function is maximized at some point, so is its logarithm. And the reason is because logarithms are monotonic functions of their arguments. So we might as well maximize the logarithm. Why is the logarithm interesting? We're going to find out that the logarithm is interesting because it's easier to work with a sum than with a product. Pound is a product. The logarithm of it will be a sum, and that will help us analyze it. So what's the logarithm of pound? The the answer is the logarithm of n factorial divided by the logarithm of n1, sorry, minus the logarithm of n1 factorial plus n2 factorial. In other words, it's just log n factorial minus the sum of the logs of the n sub I factorial. But now here the simplification happens when we use the Stirling approximation. Stirling approximation is the trick that makes all of this work and work out beautifully. So let me remind you what it is. The Stirling approximation can be written in one of two ways. It can be written as either n factorial is approximately equal to n to the n e to the minus n, or you can take its logarithm. Incidentally, if you did it numerically, you would find out that this is not all that accurate as n gets big. But if you take its logarithm, you'll find it's really accurate. The logarithm of n factorial is equal to the logarithm of n to the n, that's n log n, minus or plus the logarithm of e to the minus the n, e to the minus n. The logarithm of e to the minus n is just minus n. I think I proved this last time by doing a little integral for you. Yeah, we proved this last time, or at least motivated it. And this is what we have here, logarithms of n factorial. And so we're going to use the Stirling approximation in this form. If you actually go and numerically study these things, you find out that this formula is very accurate. This one's not so accurate. This one's, I mean, you know, you take the thing which is pretty accurate and you exponentiate it. Well, you can flop around because of the exponential, but the logarithm is a highly accurate formula. When I say it's accurate, I mean it becomes very, very good for large n. The corrections to it get smaller and smaller with large n. Okay. So let's now substitute that into here. We have this equals log of n factorial, which is n to the n.
No, n log.
No, n log n.
Can you just leave that out?
N log n minus n. That's this term here. And then we have minus the summation of n sub I log n sub I minus n sub I. That's it. Now let's work on it a little bit. Let me take it over here, and I'm going to take this piece of it over here. Let's see, I want my signs right. This one is plus, this one's minus. This one's minus, and I think this one's plus if I do it right. Or I could put a bracket around here. Minus, I put a bracket around there. Yeah. All right, let's work on this second term a little bit. The work that I'm going to do with it is very simple. I'm going to simply substitute that n is equal to capital N times p for each I. That's the same as saying n sub I over capital N is p sub I. I'm just going to plug that into here and grind it through. It's quite easy. So let's take the thing in the brackets. The thing in the brackets then is equal to each n sub I gets replaced by n times p sub I. So that's going to give you an overall factor of n. Each n sub I will be proportional to capital N. Be an overall factor of n, and then there will be a sum, and the first term and the first factor will be p of I. All right, that's the n sub I here. Then we have logarithm of n sub I. So that's logarithm of p of I times n. That's this term over here. And then we get to subtract off minus n sub I. Incidentally, I left this is fine. I think if I were really doing it right, I would have put the bracket over here. Summation n sub I log n sub I minus summation n sub I. Okay, so I won't bother writing. Yes, I will bother writing it. Minus summation of n sub I. Okay.
Why don't we just write p sub I then?
Yeah.
Where?
On the nth by, the last nth by.
Oh, I could write p sub I there. You mean leave it through the factor of n here? Yeah.
Yeah.
I could.
Yeah.
You're right. Doesn't matter. But either way, it'll the summation of. Right, so this piece, the way I've defined it, this piece does not multiply capital N, and it doesn't matter. We could do it the way you want also. The summation of n sub I is capital N, right? Okay, so let's replace this by minus capital N. And now that cancels this capital N here. Right? That one cancels this. So I think we can safely replace this and this and ignore them. Finish with that. Now what about this? Log of p times n is just log of p plus log of n. So this becomes n times summation of p of I log p of I. That's the first term. And then plus n summation over I of p of I times log n. See where that came from. The first term is gotten by just taking the log of p sub I. The second term is gotten by replacing the log here just by log of n. So that's this. Now what's the sum of p sub I? 1, which is pretty much what you would have done if you would have done it the way you said. All right, so this just goes away. And this gives us n log n. It comes in with a minus sign, and so it cancels this n log n over here. This thing is gone. All that's left is this term over here with a minus sign. The minus sign coming from here. So the whole thing is just minus n p of I log p of I, log p of I summed over I. So if we know that, if we had the probability distribution, we would count, well, not if we had a probability, it is just n p sub I log p sub I. Now, we've seen this before. Anybody remember what it is? With a minus sign, excuse me, minus sign. Entropy. It is the entropy. It's n times the entropy which appears there. Why did it come out n times the entropy? Well, the reason it came out n times the entropy is because there are n boxes. But our problem, let's take our mathematical problem now. Our mathematical problem, first of all, has a minus sign in it from here. The number of ways of rearranging things, so we're given the logarithm of the number of ways of rearranging things, to get a given set of occupation numbers is just minus n times the sum of I, p of I, this went away, log p sub I. That's it. Yes, you can remember that this is the entropy, but let's just take it for what it is. How can it possibly come out to be negative?
Log is negative.
Yeah, the log p sub I is less than 1, and so logarithm is negative.
That's your log pound?
Hmm? Yeah, that's log 10. ln, same as log. Log pound is minus n times p sub I log p sub I, and we want to maximize this whole thing, including the minus sign, we want to maximize it. In other words, we want to find out what little n's give us the most likely distribution of occupation numbers, but subject to two constraints. The first constraint is that the sum of the probabilities add up to 1. So we have to remember that when we're varying and trying to find the maximum of this, we have to keep two things fixed. We have to, the sum of the p's equal 1, and the sum of the p sub I, e sub i's is equal to e. How do we do that? Well, the answer is the method of Lagrange multipliers. We add a Lagrange multiplier for each constraint, and then later on, afterwards, we figure out what the Lagrange multipliers have to be in order to make the constraints actually satisfied. So what we do then is we take this quantity, log of pound, and remember, what is it a function of? It's either, you can think of it either as a function of the n sub i's or a function of the p sub i's. In this problem, the variables that we're maximizing with respect to are these probabilities themselves. We're trying to find the most likely probability distribution. So the p sub i's are the unknowns, and we're going to maximize this expression, log of pound, minus, now we have to put in Lagrange multipliers. The first Lagrange multiplier I will call alpha. That's the one that multiplies this constraint. Summation over I, p sub I. And the second Lagrange multiplier I'll call beta minus beta, summation over I, e sub I, p sub I. And we might as well now write in what log of pound is. Here it is right here. Oh, incidentally, one step that I didn't, we might as well throw away this in. We're trying to maximize this subject to some constraints. Well, maximizing n times something is no different than maximizing the something itself. Let's get rid of all n's. We want to maximize this thing right here, subject to the constraints that the sum of the p's is 1, and the sum of the e times p's is equal to e. So we have sum of I, p of I, log p of I with a minus sign, plus. No, minus. I think I chose the Lagrange multiplier to be minus here. Now, there's any questions up to now? Yeah.
I'm envisioning that most of the n sub i's are either 0 or 1, because
the ones which are appreciably non-zero, let's put it this way. Okay, let's think of it the following way. I think maybe it will be helpful to pretend that there is a highest energy
the
level.
NI's would be
Yeah.
proportional to n.
Yeah, yeah. But of course, yeah. But let's for simplicity suppose that there is a ceiling to the energy levels. In other words, that there are a finite number of these. And then take capital N to be much, much bigger than the total number of states. That will make sure that every n is large. So the approximation here, which seems a little bit ridiculous, but nevertheless quite legal, is to imagine the number of replicas there is larger than the number of states. And that's the approximation that, and it's not really an approximation, it's just a useful trick to keep in mind. What of course is true is that the p sub i's go to 0 as the energy gets very, very large. But we can take that into account by being very careful. The easiest way to be careful is just to truncate the energy levels at some point. Yeah.
can you just say that when the n sub i's are small, that accounts for a very small part of the sum anyway?
Yeah,
So
yeah, absolutely,
it's an absolute
absolutely,
constant.
absolutely. So that is not a problem. But as I said, the easiest way to handle it with the least number of words is just to say there's a maximum number of states, and capital N is much bigger than those. But yes, you're right. That's correct.
That doesn't seem physical. You have just one particle in a box. It can go 10 million states. And so
Yes.
you have Avogadro's number in a box. You got 10 million states times.
You can always make the number of boxes bigger than the number of states, as long as the number of states is bounded. Right? Now, in practice, the number of states is bounded because you sure don't want to have an energy in any one box which is bigger than the total energy. So in practice, there is a bound, but let's just take it simply to say that there's an upper bound here, and capital N is much bigger than that upper bound. That simplifies the argument. All right, the interesting thing is the actual mathematical argument here. Now, notice all of these are sums over I. There's no term in here, no single term in here, which involves more than one p at a time. P sub 2 doesn't ever get multiplied by p sub 1. P sub 1 gets multiplied by the logarithm of p sub 1, but it doesn't get multiplied by the logarithm of p sub 2. So this is a function which is a sum of functions of individual variables. You maximize it by maximizing it for each I separately. How do you maximize? Well, what do you do next? The next thing you do is you differentiate this with respect to p sub I, or I is a summation variable here, so let's not differentiate with respect to p sub I. Let's differentiate with respect to p sub j, where j is some specific number. P sub j enters into one term here, one term here, and one term here. J could be 46 or 59. It enters only into one term of each of these. So when we differentiate with respect to pj, let's do it. First of all, the derivative here is the sum of two terms. One is the derivative of the first factor times the second factor. That will give us a logarithm minus logarithm of p of j.
I wonder if it helps to factor p
Factor
in the
p.
first place. If it occurs in all the terms as a problem.
We can take the summation on the outside, if that's what you meant.
Why don't you take the pi outside? And then take
No, it's a sum over I.
No, but I mean,
You can't take the, no. No, you can take the summation on the outside, get rid of the sum here, get rid of the sum here. But that's it. You can't take the pi on the outside.
no, I'd say take the pi on the outside of the parentheses.
No, well, yes, yes, you can certainly take pi on the outside of the parentheses, sure. Well, do it if you like. I don't see that it helps anything. Here it is. All right, so the derivative of this term here has two terms. The first one is just logarithm of pj. That's gotten by differentiating this piece. And the other one is minus. The minus sign is all coming from this overall minus sign on the outside. So it's minus log p sub j. And then what do we get from the differentiating log? 1 over p times p, which is minus 1. Now what happens when we differentiate this term with respect to pj? We just get minus alpha. And what happens when we differentiate this term with respect to pj? We get minus beta times ej. And that all we set equal to 0. That's the method of Lagrange multipliers. Pretend that we're minimizing this whole quantity with respect to all of its variables. So for each j, we find that minus log of pj minus 1 plus alpha and so forth has to add up to 0. I can throw away the minus signs since it appears in all of them. Minus, plus, plus, plus. And now what do I have? I actually have the probability distribution, or better yet, or not better yet, but its logarithm. So, logarithm of pj equals minus 1 plus alpha, that's from here, minus beta ej. Final step, to go from the logarithm of p to p itself, we exponentiate. Exponential of the left-hand side is pj, that's pj equals e to the minus 1 plus alpha times e to the minus beta ej. Now, first of all, look at this for a little bit. This is just a number. Well, it's a number that depends on the Lagrange multiplier, but it doesn't depend on which state we're talking about. It doesn't depend on j. All of the j dependence, in other words, the dependence on which state we're talking about, is all in this factor here. And this tells us that the probability for the jth state is proportional to e to the minus this Lagrange multiplier times the energy. It tells us that the probability for different energy levels falls off exponentially as a function of the energy. That's the basic property of the Boltzmann distribution. You get a bunch of magic, a bunch of a sleight of hand, but all of it was good, genuine mathematics. And we discovered that maximizing the entropy subject to the constraint of a given total probability and a given total energy uniquely tells us that pj is proportional to e to the minus some quantity times ej. We're going to figure out soon enough what beta is. I'll tell you right now what beta is. Beta is 1 over the temperature. Or if I include Boltzmann's constant, it's 1 over k times the temperature. In most places, when I write 1 over temperature, I really mean 1 over kt. In other words, for most purposes, I will set k equal to 1 and work in units in which temperature has units of energy. Okay, so beta then is actually 1 over the temperature, proportional to 1 over the temperature. But why that's true, we have yet to establish. We have an independent definition of temperature. If you go back in your notes from the first time, there was an independent definition of temperature, which I'll remind you of, and we need to establish that they're the same thing. But for the time being, beta is a Lagrange multiplier, and we'll find out later that it's 1 over the temperature. Now, this object over here, I'm going to give another name. This is just naming things now. The Lagrange multiplier was alpha, but I'm going to give this whole thing here another name. I'm going to call it 1 divided by z. Why am I doing that? Historical. It's a historical notation. That's all. 1 divided by z. I can't help it. It replaces the Lagrange multiplier. I don't know what the Lagrange multiplier is yet. I don't know what z is yet. I haven't really done anything. I've just made a change of notation. And this I'll leave in this form. That may or may not be familiar to you. Some of you who know a little bit of statistical mechanics, this is a very famous formula. For those who don't know it, it's less famous. All right, what is z? When I say what is z, I mean what we should do now is fix the Lagrange multipliers by making sure that the constraints are satisfied. Remember, after solving the problem, we have to go back and say, let's pick the Lagrange multipliers so the constraints are satisfied. First constraint, the sums of the probabilities add up to 1. Let's see what that says. probability of the jth state is 1 divided by z. And now we want the sum over all the states, e to the minus beta. I'll now use the e sub I. This is the sum of, what is it? This is the sum of p sub I. The sum, I factored out the 1 over z from all of the terms, e to the minus beta e sub I, and the total probability has to add up to 1. Well, just by multiplying by z, that tells us what z is, at least in terms as a function of beta in any case. Remember, beta being temperature. So this gives us a formula for what z is. We still don't know what the temperature is. We don't know what beta is. But whatever beta is, that's equal to z. And z, think of it as a function of beta, or as a function of temperature. Z is called the partition function. Again, very famous formula. Z is defined by the sum. You take e to the minus beta e sub I, and you add it up for all the energy levels, and that defines the partition function. Knowing that doesn't seem like very much, the partition function. It's one little piece of, who cares what the partition function is? It's just a normalization factor that makes sure your total probabilities add up to 1. Well, in fact, as we will see as we go along, if you know the partition function, you know everything. Partition function, as a function of the variables of the problem, is a way of codifying or representing all of the thermodynamic, and even beyond the thermodynamic information, all the statistical information in your system. So this is not only an important function, it contains everything. So we'll see why. I don't expect you to see why yet. All right, how about beta? How do we choose beta? The other constraint is that the sums of the probabilities times e sub I has to add up to the average energy. Now I'm assuming that we know the average energy. The whole ensemble of copies had a total fixed amount of energy. If I just divide it by n, that tells me what the energy of each replica is, of each copy. So I will assume for the moment that I know what E is, E bar, or the average energy of one copy. Let's write down the formula. Summation over I is again a 1 over z on the outside. That's because each p sub I has a 1 over z. And then there is e to the minus beta e sub I. If that's not finished, we have to multiply by e sub I. And that's equal to the average energy. Now, it would be simple to say, look, this does determine what beta is. This is an equation for beta. I already know what z is in terms of beta. So this is an equation. If I know E bar, this is a relationship between the temperature, if you like, and the average energy. But we can do a slick thing with this. We can actually express all of this nicely in terms of the partition function itself. So let's see. Let's find another blackboard here and do that. This is the object here whose sum defines the partition function. But we have an extra e sub I here. The trick, this is a trick, but this is such a standard trick that by this point, well, anybody who has done a little bit of mathematics from time to time would rather quickly realize that the next step is to replace the e sub I by the derivative with respect to beta. If I have a thing like e to the minus beta times e, and I want to multiply it, any e, and I want to multiply it by e, one way of doing it is just to differentiate it with respect to beta, and then we have to change the sign. The derivative with respect to beta of an exponential e to the minus beta e is just e times the exponential. Not this e, this e. This is equal to e times e to the minus beta e. All right, so every place here where you see e times e to the minus beta e, let's write it as 1 over z, sum on I, derivative with respect to beta. I'm going to write it as partial derivative with respect to beta. The reason is, later on, not now, but later on there are going to be more variables in the problem. Volume, magnetic field, all sorts of things. And I mean differentiate, keeping all those other things fixed. For our purposes here, I could just use ordinary derivatives. But later on, we'll want to remember there may be more variables in the problem, and now I mean differentiating with respect to beta, keeping all the other things in the problem fixed, of e to the minus beta e sub I, period. Now,
Minus sign.
minus sign, thank you. Now, the derivative can be taken outside the sum. The sum of derivatives is the derivative of the sum. Right? So the derivative can be taken out on the outside. Let's take it on the outside. It becomes d by d beta of the sum. And what is this? This is the partition function. So we have a lovely formula now. That the average energy is equal to minus 1 upon z, derivative of z with respect to beta. Beta, remember, is the inverse temperature. So again, if you know the partition function as a function of beta, then, here it is, z of beta, then all you have to do is construct 1 over z times the derivative of z with respect to beta. At that temperature, that will give you the average energy. This gives you a relationship between average energy, or just energy, let's call it, and the temperature. The right-hand side is a function of temperature. The left-hand side is the average energy. This can be rewritten as minus the derivative of logarithm of z with respect to beta. 1 over z, dz by d beta, is the derivative of logarithm of z. The logarithm of z occurs over and over and over again. And it occurs so much that we give it a special name. That's the average energy. Oh, before we talk about the name of this thing, let's just see what it says. The left-hand side is a well-defined, I mean, if we can calculate, to the extent that we can calculate z of beta. It's a function of beta, and a function of beta is equal to the energy. We can invert that, and we can find out what beta is as a function of the energy. Whatever that relationship is, if we can invert it, we can find out beta as a function of the energy. Beta is the Lagrange multiplier, but it is also the inverse temperature. So this is the relationship between temperature and energy. In many examples, we actually won't want to invert this. We may know the temperature, in which case we may be more interested, we know the temperature, we may be more interested in finding the energy. In some cases, we may know the energy, and we may be interested in finding out what the temperature is at that energy. This formula, together with the formula that z is summation of e to the minus beta e sub I, g of beta, that, as I said, contains a good deal of information, more than a good deal, just endless amounts of information about the statistical system. Let's see what we're going to... Yes, I told you that logarithm of z has a special name. Let me just get the signs right. I think T, temperature times logarithm of Z with a minus sign, which is the same as logarithm of Z divided by beta. Anybody know what that's called? With a minus sign. Before I tell you its name, let's just notice Z is not itself actually a single exponential, but it sort of looks like an exponential of beta times energy. If I take the logarithm of Z, I expect it to have at least have units or be similar to beta times some kind of thing that I might call a thing which has units of energy. So the logarithm of Z is sort of like what's up here. It's not really, but I mean, it's sort of like the sort of thing which goes in the exponent here. And if I divide it by beta, then it's some kind of thing which has units of energy. The logarithm of Z divided by beta has units of energy. Of course, really Z is the sum of such terms, but that doesn't prevent us from calling this kind of energy. It is what it is. It is not the energy of the system, it's the Helm-Holtz free energy, it's called. A is the Helm-Holtz free energy. As units of energy, and it's just minus the logarithm of Z divided by beta. Why minus the logarithm? Because the exponential here carries a minus with it. So it's natural to put a minus in front of it. All right, so that's definition. There's no proof of that. That's the definition of A, the Helmholtz free energy. Okay, what is not definition is a relationship between the energy, the Helmholtz free energy, and the entropy. We've defined entropy already. We certainly know what energy is, and we now have a definition of the Helmholtz free energy. There is a relationship between the three of these things, energy, entropy, and Helmholtz free energy, which we should derive. It's easy enough to derive. You might be saying to yourself by this point already, when the hell are we going to get to molecules and gas? The answer is pretty soon. But it is worth exploring the general mathematics before we do particular systems. Once we have some mathematics in place, once we know and understand how to use this partition function as a generator of all kinds of answers, we will have a machine that we can mindlessly use to crank out all kinds of things about statistical mechanical systems. So it's worth exploring the general principles before we actually try to attack a system. Let's just see what we have. Helmholtz free energy is equal to logarithm of Z divided by beta. And let me just write down next to it here, the energy itself, that was not by definition, but by calculation, was equal to minus the derivative of the logarithm of Z with respect to beta. They're kind of similar. One is actually the logarithm of Z divided by beta, and the other is the derivative of the logarithm of Z with respect to beta. They're not the same thing. Right? If Z, well, you could see that they're not the same thing, but they have some relationship to each other. If logarithm of Z was a straight line, which it is in general not, but if it were a straight line as a function of beta, then they would be the same. But of course, they're not. It's not a straight line in general. All right, those are the two important quantities. And one more quantity is the entropy. So let's calculate the entropy. And we're going to find that the entropy is closely related to A and E, and of course, beta. What is the entropy? The entropy is minus the sum of p sub I logarithm of p sub I. But now we know what p sub I is. We know that it's just up there, 1 over z e to the minus beta ei for p sub I. So let's plug that in and grind away and calculate what the entropy is. Maybe we'll get stuck and we won't be able to do it in any useful or interesting way. We can just do the sum, of course, but maybe we'll get somewheres. So let's try it. S is equal to minus. Now what's p sub I? 1 over z is a sum on the outside. 1 over z times e to the minus beta e sub I. And now what's the logarithm of p sub I? It's the logarithm of that expression up there, except change j to I. The logarithm of that is minus beta e sub I. That's the logarithm of the second factor, the exponential, and then we have to subtract off minus log z. I need a stick. I don't have a stick to point with. Okay, does everybody see what I've done? I've written p sub I as 1 over z e to the minus beta e sub I, and then logarithm of p sub I as minus beta e sub I minus log z. That's S. The minus sign goes away. I've taken the minus sign, the overall minus sign, and the minus signs here and canceled them. Okay, what's the first term? 1 over z e to the minus beta e sub I times beta e sub I. Suppose the beta wasn't there first. That's the average energy. That's the average energy. So we can say that S is equal, the first term is just the average energy, times beta. Sorry, times beta. It's this beta over here. And what about the second term? The second term, there's no I dependence in here. This is just logarithm of z. That doesn't depend on I at all. So in doing the sum here, all we're doing is summing e to the minus beta e sub I. What is that? Sum of e to the minus beta e sub I. Z. And that cancels the z here. So all we're left with is logarithm of z plus log of z. Go over that again. We've taken care of the first term here. That was just the average energy. The second term, we can factor out the log of z on the outside. It's log of z. And then it's just the sum of 1 over z e to the minus beta e sub I. That's just 1. That's just 1. So that's it. What do we have? We now have a formula relating entropy, energy, and Helmholtz free energy. The Helmholtz free energy, I don't want to erase it in this form. Let's just put it up here. And again, logarithm of z is minus beta times a. So here we have it. S is equal to beta times e minus a. So the Helmholtz free energy, or the difference between the energy and the Helmholtz free energy is just the entropy, or the entropy divided by beta. Another way we can write it, by using that beta is 1 over temperature, we can write it as Ts is equal to E minus A. So whatever the Helmholtz free energy is, the difference between it and the real energy is just, or the average energy, is just temperature times entropy. This allows us to express the entropy in terms of the partition function. Let's see what it is. We have to take E minus A. So E minus A is well, it's the logarithm of z divided by beta minus derivative of the log of z with respect to beta. This is what the entropy is. This is a formula for the entropy. I don't mean this is not the definition of the entropy. A, and that's equal to Ts. Do I have that right? If I'm lucky, the temperature will cancel from this one. Yeah. This is also 1 over beta. All right, so we can multiply by beta if we like. Multiply by beta, another form, S is equal to log z minus beta d log z by d beta. Whole bunch of formulas. The main upshot is when you know z, you have tools for calculating energy, entropy, Helm-Holtz free energy if it means anything to you, which it will, because we will use it for all sorts of applications. Thus far, I haven't told you what it's good for, other than calculating the entropy from the energy. But you can see that there's some power in knowing the partition function. Each one of the various thermodynamic variables can be represented fairly easily in terms of the logarithm of z. It's always the logarithm of z which comes into things. So the logarithm of z is often more interesting than z itself. Question?
Well, I haven't really demonstrated that the probability is so.
Yeah, we haven't. We haven't. The way to demonstrate
Variance
it.
or something?
What's that?
You have to compute like a variance or something?
Yeah, it's a variance. Okay, good. I was going to jump into the ideal gas, but before we do that, let's do variances, statistical fluctuations, and see if we can learn something about the size of statistical fluctuations. What we'll find is that they're very small, but let's see if we can do that. We have our choice now, either to jump into an application, which is theory of gas and so forth, or to do a little more theory, the more theory being theory of fluctuations. And the theory of fluctuations is sort of general theory. The theory of gases is a special case. Which would you rather do? Fluctuations. I mean, it's awfully interesting, and so are gases, but less general. All right, let's do fluctuations. Let's take a quantity, let's call it x. X is, of course, a thing which has a value for each state of the system. For each state of the system, x has some value. And I'm interested in the probability distribution, I'm interested in the variance of x. Or if you like, let's call it the uncertainty or the fluctuation in x. The fluctuation in x, how do we define it? Well, I'll give you a definition. The definition is, first of all, subtract from x its average. So subtract from x its average value. So if we have a probability distribution for x which looks like that, we subtract the average value, which is in here somewheres, and that effectively just moves the probability distribution so that the center of the probability distribution, or the average of the probability distribution, is now located at 0. Other than that, an x bar does not depend on I, it's just a number, just a number. Now we take this and we square it. And then we take the average of the whole thing. So we have some probability distribution which is centered at the origin. It's centered at the origin because I've shifted it. We take x squared and we average it, and that gives us, that is a measure of the width of the distribution. It's always positive because it's a square of something, and when averaged, it's always positive, and it measures the width of the distribution. All right, we call it the variance. mean square, root mean square, something or other. Yeah. So that's the statistical variance in X, and I want to calculate it for, well, first of all, let me simplify it, or let me re-express it. First of all, this can be expressed as the average. Incidentally, the overbar and the bracket notation are the same thing. I just didn't want to write brackets inside brackets. All right, so what is this? First of all, let's take the thing inside the bracket. It's X squared minus twice X times X bar plus X bar squared. If you like, call this X of I, X of I. And now we have to average this. First of all, what's the average of X sub I squared? Well, it's just the average of X squared. So this here is just the average of X squared. First term. What about the average of X bar squared? It's just X bar squared. X bar doesn't depend on I, it's just a number as far as I is concerned. And averaging a number is just the number. So this gives us plus X bar squared. Now, notice, I'll deal with this one in a moment, but notice this is not the same as this. This is the average of the square, this is the square of the average. Okay, two different things. The square of the average of the square. And then what about this one? What's the average of this? It's just minus 2 X bar squared. Averaging X gives you X bar, and it just multiplies this X bar, so it's minus twice X bar squared. Two of these, one over here, the result is just X, this one squared, minus this one. All right, so this is a standard statistical fact that the variance in a variable is the difference between the average of the square and the square of the average. If I want to write it in a single notation, I will write it this way. The difference of the average of the square and the square of the average. That's the variance. For a narrow distribution, when the distribution is narrowly peaked, this is small. The smaller it is, the narrower the distribution. So let's try to calculate. Let's see how smart we can be and see if we can calculate the variance in the energy. We'll try to calculate the variance in the energy. What would it mean, incidentally, for the distribution to be sharply peaked? It would mean that the variance in the energy is much smaller than the energy itself. Or I guess we would call this the square of the variance. We call this the variance or the square of the variance?
That's right.
Call it the variance? All right. But it's also the square of the uncertainty in X, if you like. It's the square of the width of the distribution. So we might want to compare this quantity here with the square of the energy itself. In other words, we might want to compare the difference of these two to either one of them separately. When that's small, we say that the peak is sharp. But let's see how well we can do. How far can we go in calculating this variance for energy? We've calculated the average of the energy. Let's write down the formula. The average, there it is right here. But let me write up here. The energy is equal to minus d log z with respect to beta. Let's see if we can calculate the average of the square of the energy. This is the average energy. Now I'm going to use the fact that it really was the average of the energy. Most of the times I don't bother writing this average, but this is the average of the energy. Minus d log z by the beta. We'll wind up squaring it because we're instructed to square it over here. But first, let's calculate the average of the square of the energy. So for that we need a formula for this average of the square. Average of the square of the energy is P of I times E sub I squared. That's the average of the square of the energy, which is equal to 1 over z sum e to the minus beta E sub I, that's P sub I, times E sub I squared. Remember what I did to find the average energy. In that case we only had one power of energy here. We just differentiated with respect to beta to bring down that E here. What should I do to get to E squared?
Second derivative.
Take the second derivative. When I take the second derivative, we'll find out that the average of E squared is just 1 over z times the second derivative of z with respect to beta squared, correct? I think now there's no minus sign.
Is it Z or log Z?
Z. Z. E squared, it gives you two derivatives.
Okay.
Right. Z squared. Okay. Now I can write down the variance. The variance is, first of all, this term, 1 over z, d second z by d beta squared. And now we have to subtract the average of E squared, which is minus d log of z by d beta squared. In fact, let me write this slightly differently. D log z by d beta is 1 over z dz by d beta. So actually this is just 1 over z squared, 1 over z squared dz by d beta, 1 over z squared dz by d beta, 1 over z dz by d beta squared. So it's the difference between 1 over z times the second derivative of z with respect to beta minus 1 over z squared dz by d beta squared. That's the variance. We're not finished with it yet. This is simpler than it looks. Let's see. This is, I believe, I think it's just the second, let's try it out. The second derivative of log z with respect to beta is, I think, what it is. Let's try it out and find out. The derivative of log z with respect to beta, let's see. The derivative of log z with respect to beta, that's 1 over z dz by d beta. That's the first derivative. And now we want to differentiate it again with respect to beta. All right, so what happens when we differentiate this product here with respect to beta? I get one term, which is 1 over z times the second derivative of z with respect to beta. That's here. Now what's the other term when I differentiate 1 over z with respect to beta? That gives me 1 minus 1 over z squared, another factor, two factors of dz d beta. Is that clear? When I differentiate, forget this here for a moment, let's put it over here. dz by d beta. When I differentiate 1 over z with respect to beta, I get minus 1 over z squared, another dz by d beta. And so that gives me this term here. So here's what I found. I found out that the variance is just the second derivative of log z with respect to beta. Okay, let's examine it a little more closely. z by d beta that's equal to minus the energy. So what this whole thing is, I mean, we've made a number of steps. Whenever I do this, I always feel like I've done too many steps. Like I've done the same steps backward and forward and back. Yeah.
Would you mind giving a physical interpretation of Z? I'm kind of lost as to what Z, I know it's part of the solution of alpha for the Lagrange, but I don't have a sense of physically what it is. It's not a constant.
No, it's a function of beta.
It's a function of beta.
And whatever it is, it contains all the information about the thermodynamics.
Okay.
It's a thing which you differentiate, you take its logarithm, you do all sorts of tricks with it, and it generates the full thermodynamics. What can I tell you? It's the free energy, or its logarithm is the free energy, or its logarithm divided by beta. We're going to calculate these things over and over, and eventually you'll get some sense for what it is. But there's no...
Is it an intermediate type of variable?
Well, it's a generating function.
Generating.
It's a generating function that generates lots of answers. You do things to it. You know what it is? It's the Laplace transform of, what is it, the Laplace transform? It's the Laplace transform of the density of states. Does that help you at all?
Thank you.
It doesn't have a simple interpretation, something you can measure. It's something you do something to generate answers. The action in mechanics is a thing that you do things to generate equations of motion and so forth. The partition function is also a generating function that you do various operations, and just about everything you can think of in thermodynamics. And fluctuations take us beyond thermodynamics, incidentally. So,
What are the units of Z?
say it again?
The units of Z.
Z is dimensionless. Z is dimensionless. Things in exponents are always dimensionless. So when you sum things in exponents, it's always dimensionless. Right. So it has no units. I would say, rather than saying what its physical interpretation is, which means, I suppose that means, how does it relate to measurable quantities? Is it a measurable quantity? No, it's not in itself directly a measurable quantity. It's not what its physical interpretation is. It's what you can do with it to generate things whose physical interpretation you do know. Okay, so we'll play with it a lot. But in any case, we now see that we can calculate the fluctuations in the energy as well as the energy itself. But let's do a little more with it. We're calculating the I guess I can call it the fluctuation in energy squared. Let's think of it that way. Uncertainty, or the spread in the energy squared. And what we find out is that it's the second derivative of log z with respect to beta squared. All right, now the first derivative of log z is just the energy, or minus the energy, and so we have d by d beta of the energy. Now what is beta? Beta is 1 over temperature. So this can be related to the derivative of the energy with respect to temperature. This is dE d beta, which is dE by dt, temperature, times d temperature, d beta. But beta is just 1 over temperature. So what's the dt d beta? 1 over t squared, right? Minus 1 over t squared. No. T squared, t squared. T squared. T by d beta, let's write that out. T is equal to 1 over beta. dt by d beta is equal to minus 1 over beta squared, which is equal to minus t squared. Okay, so did I lose a minus sign?
Never mind, fine.
Here it is. The t by d beta is just minus, that gets rid of a minus, and this becomes t squared upstairs. Now, what is this? The e by dt. It's got a name.
Just a second.
The heat capacity. It's the heat capacity. The heat capacity, the E by dt, is the heat capacity. It's the definition of the heat capacity. It's the amount of, well, no,
What is it? Amount of energy needed for delta T. Amount of energy accumulated
yeah,
for delta
amount of
T.
energy to change the temperature by 1 unit. Okay. How much energy do you have to put in to change the energy by 1 unit?
Could we go back just a second here?
Yes.
Oh, we showed that the delta E squared is the second derivative of log z with respect to beta squared.
Right.
Okay, now where do we get from, how do we get?
The first derivative is just the energy.
Right.
The log z by d beta, apart from the sign, the log z by d beta is energy. So the answer is the derivative of energy with respect to beta.
The log z with, okay, so I see what you're
Yeah,
saying.
the equation is right there.
Upward, E equals.
Yeah. The first derivative is just the energy.
Beta.
Right. Now I want to differentiate this again with respect to beta. So it's just the E by d beta. Which if I decide I would like to use temperature instead of, just for familiarity's sake, if I like temperature better than beta, which I do, I mean, sense of temperature, I substitute the E d beta dt, and it gives me t squared times the specific heat, not the specific heat. I always say specific heat when I mean capacity. Heat capacity, t squared times the heat capacity. Okay, first of all, how does the heat capacity grow with the number of particles in a system? Remember what it is now, or the size of the system. Let's say the number of particles. It's the amount of heat that you need to change the temperature by 1 unit. It's proportional to the number of particles in the system. The bigger the system, the heavier the system, the more energy you have to put in to change the temperature by a given amount. And in fact, the heat capacity is proportional to the mass of the system, depending on what you use. Let's just say the number of particles in the system. So the right-hand side here is proportional to the number of particles. What about the energy itself? Also proportional to the number of particles. But the square of energies, what we should compare it with, is the square of the energy. It has the units of squares of energy. The square of the energy is proportional to the square of the number of particles. So in that sense, the fluctuation is very much smaller than the energy itself. We should take the square root of both sides in order to have a fluctuation in the energy. The uncertainty in the energy is T times the square root of the heat capacity. Heat capacities grow linearly with the number of particles in the system. So this side here grows like the square root of the number of particles, but the energy itself grows linearly with the number of particles. So the fluctuation divided by the quantity itself gets smaller and smaller, like 1 divided by the square root of the number of particles. That's the demonstration, if you like, that fluctuations are small by comparison with the quantities themselves. So that's one way of seeing it. I might also add one more point. Let's keep track. I rarely keep track of Boltzmann's constant. Okay, but let's keep track of Boltzmann's constant for a little bit. In order to keep track of Boltzmann's constant, I'll give you some standard let's call them undergraduate textbook definition. According to the standard undergraduate textbook definition, I'll call it temperature little t. And little t is such that it times the Boltzmann constant is what I call big T. That's the definition of Boltzmann, or if you like, that's where the Boltzmann constant comes in. And also the standard undergraduate textbook definition of entropy, which I will call little s, you also multiply that by K Boltzmann to get what I call big S, what I call entropy. No decent information theoretic physicist would ever define anything except this, except if you're trying to compare things to a definition of entropy which was in some ancient textbook. Then you would put a K Boltzmann. Notice that K Boltzmann will cancel out, let's see, do I have this right? Do I have this upside down? KT is what I call temperature. Well, let's see. The E equals TdS, which should equal little t d little s. So I think I have this upside down. I think it's K Boltzmann in the denominator. Yeah, I think that's right. This is standard textbook definition. And it's such that when you write that the E equals TdS, it's the same as writing it in the undergraduate textbook sense. The K Boltzmann's cancel. Just engineer the definition of entropy so that they cancel out of here. T times S, the Boltzmann cancel. Yeah, that's correct. These are standard definitions.
Is it very hard to prove that beta is 1 over T?
We're going to do it at some point. It's in the notes, and we're going to do it.
Okay.
But at the moment, let it be a definition.
Okay.
Yeah. Well, that's a definition, but this was also a definition.
Yeah.
We have two definitions. They could clash. They don't.
Okay.
So yeah, we'll do that, but not now. Right. Now let's go back to this formula over here that the uncertainty in the energy squared is equal to T squared times the heat capacity, which is what? It's dE by dt. Does this formula make dimensional sense? Well, it does make, yeah, it makes a dimensional sense. But where does the Boltzmann constant go into this? The answer is wherever you see capital T, and you want to use, let's call it undergraduate physics notation, put K times little t. So that means that we can put little t here, little t squared, little t here, and then I think there's one K Boltzmann in the numerator here. This is in fact the first place in anything we've discussed where K Boltzmann actually appears. K Boltzmann appears in fluctuations. This is the heat capacity. It's a thing you measure in the laboratory. It's neither terribly small nor terribly big. It's just whatever energy it takes, how much heat, how many BTUs, or how many calories, or how many joules you have to pump in to change the temperature by a certain amount. So this is neither a terribly small quantity nor a very big quantity. This temperature could be room temperature, 300 degrees or whatever. It's also not a very big number or a small number. We do expect for a big box of gas, for a mole of gas, for example, we expect the fluctuations in energy to be very small, at least by comparison with the energy itself. Here's another source of smallness. K Boltzmann is a very small number. How small? 10 to the minus 23rd. All right? So this number is 10 to the minus 23rd. 1.4 times 10 to the minus 23rd, or something like that. And so this tells us for a mole of gas, the fluctuations in the energy at a reasonable temperature are very, very small for no other reason because K Boltzmann appears in the formula. So Yeah, fluctuations are small. Probability distributions are highly peaked when the number of particles becomes large.
I think that's not the same C as the other one.
Yeah, it was, I think.
Well, the other one was the E by big T.
Oh, you're right. So what
There's
happened?
another, maybe cancel.
No, KB shouldn't cancel.
Oh,
Um, I don't think it should.
oh, right, there's a square root. No,
Yeah. The e dt, the other e squared is equal to the e dt times t squared, right? No.
KB in the denominator is T.
Okay, let's put t here, and that would put a kb here, right?
Yeah.
And then p squared would be p squared times kb squared, right?
Yeah, you have the right thing, it's just
Yeah.
that what you wrote C as equal to is the E by the big T.
Oh, you're right. The standard definition of heat capacity is dE by d little t. All right? So, you're right. I was careless. Okay, so here we have it. 2 kBs in the numerator, 1 kB in the denominator, and this is the thing that you would normally call heat capacity, dE by d little t.
Okay.
Right, good, thank you. Very good. All right, so we see two senses in which, first of all, it's got a numerical constant in front of it, which is very small. But in the second sense, it's also true that the fluctuation in energy only grows as the square root of the number of particles, whereas the energy itself typically grows as the number of particles itself. That's characteristic, of course, of fluctuation growing as square root of the quantity that's the fluctuation of. So that's the sense in which the probability distribution is narrow. Well, let's see. I think that's a good place to stop. I really have. Oh. We have 15 more minutes. The next time we are going to go into the theory of the ideal gas and not so ideal gas and do some things with it. But let me just... No, I think we're going to stop here. Let's stop and field some questions, and if there are no questions, yeah. I think we should leave a little bit early today because I didn't get my cookie.
I had a dog and pony show with the bankers today.
Yeah. My wife, who doesn't know anything about computers, gets very, very annoyed when the computer, when some things happen, it says, your cookie has been deleted. I also don't know what a cookie is, but I don't get so annoyed. I know my cookie was deleted. Okay, if there are no questions, other questions?
I have one question from last week.
Yeah.
You said the quantities that are conserved like charge, they actually think the total quantity in the universe is 0. And
Oh, well, that's when, yeah, okay, I did say that.
last week,
Yeah.
I think he said the same thing with energy.
Yeah.
So where's the negative?
In a closed universe.
Okay, okay.
Closed
In
universe, yeah.
a closed universe.
Yeah.
So I see all sorts of positive energy. I don't see any negative energy.
No, the negative energy
There
is A dot over A squared term in the expansion of the universe. It's the kinetic energy of expansion of space. Yeah. And it's purely got to do with geometry, the expanding geometry of space, and it's the term that corresponds to the gravitational energy.
Gravitational energy is negative.
The energy stored in the gravitational field.
Okay.
And the gravitational field is geometry. In this case, the geometry is four-dimensional geometry. Spatial geometry is expanding. That means the four-dimensional geometry is something that looks like that.
Okay.
expanding, it's not flat, it's not good old flat space. It has some energy of its own, and that's the
And that's associated with gravitational fields.
associated with gravitational fields. If all the other energies are positive, it forces the universe to expand.
I see.
Yeah.
What about information? You were saying that was more fundamental, but it seems like all the information of all the bubbles was in this one at the beginning.
All the information in what?
For all the bubbles in the eternal inflation.
Wait, are we going in there? Let's not go there now, I'm too hungry. Somebody wanted to ask me a question about the lecture you wanted to ask a question about Alex's lecture, about Lincoln's lecture.
Oh, that was that question. He said that the total energy was zero. Another thing is the argument for a closed universe, when the total charge energy is zero, is it sort of all the lines of force came back.
Yeah.
Why doesn't that work for mass? Let's say we have a closed universe.
Mass is energy.
Okay. So you would have gravitational lines. And
Yeah.
would they not all converge the same way that?
No, you have to keep in mind that there's a gravitational component to the energy. That's not. There's only one conservation law. It's energy. Mass is not conserved in relativistic physics. Mass itself is not conserved. I say there's only one conservation law. There are many conservation laws, but energy and mass are not separate conservation laws.
Right.
In the general context, it's just energy. And energy has various components. In addition to all the usual stuff, which by itself is not conserved, in an expanding universe, the ordinary components of the energy are not conserved. And the non-conservation is compensated for by a change in the gravitational energy. That's this.
Okay.
Yeah. So you can either say that in general relativity there's no concept of conservation of energy, or you can keep track of pieces of the energy which are a little unfamiliar, and then you would say not only is it conserved, but it's exactly zero.
Didn't he say the cosmic horizon is 40 billion light years away?
He's probably more accurate than I was.
In earlier time, that things that are now 40 billion light years away could affect our current universe. You can still see them. Okay.
Yeah. He's probably good. Yeah, he's probably more accurate. 15 was an order of magnitude within a factor of 3. No, I'm sure he's right. I didn't sit down and calculate it.
I think basically the difference is that there isn't some expansion since the light that's furthest away is reaching.
Of course.
Yeah, that's what makes that difference.
About a basic understanding of this Boltzmann distribution.
Boltzmann distribution, yes.
If I increase energy,
If you increase, let's see.
it's up to the top board where we have the distribution of the DI. Okay, that's DJ. It seems that the lowest energy state is always going to have the highest.
Yes, it does.
So what we have is this long tip that gets longer as the energy goes up. The ground state always is the one that has the largest options.
Yeah, okay, but, right, that is correct. That is correct. So, let's put T in over here. At very, very low temperatures, the probability distribution is sort of squashed toward very low energy. As the temperature goes up and you go to enormously high temperatures, what happens? What happens, and these are of course the states, these are all states. The distribution gets flat. All states become equally probable at infinite temperature. At infinite temperature, That's a state of absolute maximum entropy that you can possibly have, infinite temperature. You know nothing about the system, so all are... All right. Now there's another element here. The typical states of a system are not equally spaced like this. If you were to write not state number here, I, but energy, you would find out that the low energy states are fairly well separated from each other, and they get denser and denser and denser and denser and denser. So if you asked about the probability for a given energy, not the probability for the ith state, you would find out that tilts it toward higher energies because there are just more states with higher energy. There are many, many more states with higher energy than there are with lower energy. So if you wanted to know what the probability is that the energy is between two limits here, you would have to say at a given temperature, you would take the probability that you're in the ith state and multiply it by the number of states in that narrow bin. And that narrow bin gets more and more states. You understand what I'm saying? You get more what?
You get more.
There are more states. There are more states within a given range of energy. Let's say within a given range of energy, delta E over here, and delta E over here. There are just many, many more states here than there are here.
Right. So the curves then come up. So there's going to be more things.
It depends on what you're plotting. If you're plotting the probability for the ith state, then it's just flat. But if you're calculating the probability for a given energy, then it's tilted up.
Have you ever had a system where you get a different kind of distribution where you figure out those low energy states, everything just picks up?
You mean,
Very speculative, but
you're asking whether there's any interesting situations where the probability, let's plot here the ith state, not the energy itself, where the probability distribution might look like that. Well, it won't be equilibrium. It won't be equilibrium. It won't be equilibrium. But you can see from this, incidentally, why it is that both the energy and the entropy increase monotonically with temperature. What happens as temperature increases? At low temperatures, the distribution looks like that. At higher temperatures, the distribution gets spread. At higher temperatures, the distribution gets spread. It's completely obvious that the average energy grows. Well, why does the average entropy grow? Remember what entropy is. It's the width, it's the average number of states contained within the distribution. As the distribution gets flatter and flatter, it contains more states with significant probability. So both the entropy and the energy are typically monotonically increasing functions of the temperature. Temperature goes up, energy goes up, entropy goes up.
You know, pump laser, an example of a situation you get that kind of population inversion?
Yes. And in those cases, you get negative temperature. We can talk about that next time. Yeah. But of course, if you take the laser, really isn't a system in thermal equilibrium with its environment and everything else. It's a, but yes, the answer is yes.
Question about the EI. The EI is some number proportional to I, I assume. Is that correct?
What do you mean proportional to I? Proportional, you mean linear?
Yeah, because you numerous.
No, these states are not really equally spaced like that in energy.
And what determines how they're spaced?
The system itself. A quantum mechanical particle in a box would have a level density which is denser and denser.
Okay.
No, I mean that's something you have to know what the system is.
So we have to answer. That's a characteristic of the system.
That's hydrogen. That lines of hydrogen.
I can tell you what the
for a gas.
All right. Well, I will tell you now what another way. The answer is that the density of states, usually called rho of E, is the number of states per unit energy. It's the number of states, let's call it delta N divided by delta E. This is number of states. That's E to the entropy. well, we haven't proved that, but that's a fact, that e to the entropy is the density of states for most systems. And so since entropy is an increasing function of energy, the density of states is also practically an increasing function of
So for a gas, then would have some characteristic distribution.
oh yeah. Yeah, we'll calculate that distribution. It's equivalent to calculating the entropy. That's not obvious, just it is true.
One question here. Did Boltzmann actually postulate that there was some sort of fundamental size of energy, or did he assume that there was a continuous?
No, he assumed there was a continuous spectrum of energies.
So it was a little different, is there?
Yeah, a little bit. But we're going to get into that next time. Next time we will have to talk, we're not going to be thinking about quantum mechanics, we will have to talk about what happens when the energy distribution is continuous. Okay.
For more, please visit us at stanford.edu.